7 sections in this chapter. I think as we look at this week, we don't have a quiz or a test this week. So I know you guys will be disappointed by that. No assessments this week. And then next week, I don't know, I'll have to look at when I have the quiz. I can't remember if it's after section 4 or after section 5. Usually it's about halfway through. But we're probably going to be looking at it, our next quiz probably middle of next week sometime. Okay? Because we don't have school Monday again next week. All right, so section 2.1. Hey, this section is going to be a little bit different. I'm going to kind of introduce you to a few things that we haven't seen before. The first thing that it talks about are a lot of different types of functions. I told you early on in the semester that one thing that college algebra does is it focuses on a lot of different kinds of functions, a lot of different types of graphs. And we've already seen some of those. We didn't necessarily talk about what type of function it was, but linear was a big one. We did quadratic a bunch in chapter 1. We saw some of the other ones, like more on our calculator, putting into our calculator. But when I see specific symbols, then what kind of graph does it make? And the graph is going to stay pretty consistent for the type of function that it is. And so we're going to kind of introduce you to some of those today. A lot of these are going to look familiar to you because you've seen most of these before. There might be a couple of them that are not quite so familiar to us. All right, so the very first one is linear. Linear is in the basic form of y equals x. You could even say y equals mx plus b, but just for real basic purposes here, I'm just going to say y equals x. And if I look at a graph of it, it's just going to make a line. Linear equation is going to make a line. And we looked at like horizontal and vertical, so there's different kinds of lines that might be made. But here we're looking at one that has some slope to it. Okay, the other one we saw a lot of in chapter 1 was quadratic. So these are the two that we've probably seen the most, especially this year, but even in years past. The generic form for a quadratic equation always has an exponent of 2. Y equals x squared. What kind of basic shape does quadratic equation make? It's the U shape, okay? We call it a parabola, and it's just going to make... And we've seen some that open down and some that open up. Sometimes they're a little bit wider and sometimes they're skinnier, and we'll talk about all those things later. But right now we're just talking about what basic shape is it making. Okay, the third function is what we call the cubic function, and we're going to have 6 of these total, 6 different functions. So quadratic is always squared, has an exponent of 2. Cubic is always raised to the third power. A cubic graph, I call it the snake-like graph because it kind of makes like a snake-like path. It doesn't have to go through the origin, but we're just talking about the real basic function. If you were to type this into your calculator, it should give you a graph that looks basically like that. Okay, and we're just looking at the basic graphs. Like as we start to throw numbers and things like that in here, then it's still going to make that same shape, but it might look just a little bit different based on what numbers we're going to throw in there with it. Okay, the fourth one is what we call the square root function. Okay, it has a square root in its equation. We saw a couple of these last chapter when we were talking about like domain and range, and this was one of those questions where we would put it into our calculator we would get a graph of it, we would see what it looks like, and then we would try to determine what the domain and range of that graph would be. In this case, the basic square root function is going to start at 0, 0, and it's going to kind of curve out to the right. Okay, the fifth one is what we call the reciprocal function. And what's happening here is what are we doing to x, right? Are we squaring it? Are we cubing it? Are we taking the square root of x? So every time we're doing something to the x. So in this case, we're taking the reciprocal of x. That's why we call it the reciprocal function. We flip it over, and we write it as 1 over x. This is one you probably saw a little bit of in Algebra 2, but it's been a while. And what this graph is going to look like, and once again, you could put this into the calculator pretty easily. I'm just doing a real basic sketch of what this looks like. But you have like two different branches. You have two different parts of your graph that are in opposite corners of your coordinate plane. If I were to put like a negative here, then my branches would be in the other two opposite corners from one another. So it could change things up to what's going on. But basically you have two different branches. Your x and your y-axis are what we call asymptotes, where it's approaching the x and y-axis from two different directions, but never crossing those two axes either. And so it's just going to get really, really close to it. Okay, and then the last one we're going to talk about today is the absolute value function. And the names of these all pretty much tell you what's going on. Here we're taking the absolute value of x. This is another one we saw a little bit in chapter 1. It would be one of those where we would put it into our calculator. I kind of showed you where you would go in your calculator to put in that absolute value function into your calculator when we were graphing it. And this one made a V instead of a U. So it would come down, hit, and go back up. Okay, so kind of similar to a quadratic, except they're not curves, they're lines. Okay, so those are your 6 main functions. Okay, what you're going to see on like the first 8 problems of your homework today is they're going to give you an example of one of these functions. And you're going to have to determine which one of these functions do we have. So I'll just give you a couple of examples here of some of these and kind of show you what they're looking for here. Okay, so if I were to write this one out, y equals 3x plus 4. And all that it's asking here is, what is the generic function that we're doing? So what would we say here? What type of function is this? It's linear, right? And so linear is the name for it. The generic equation is y equals x. And it's just asking for the basic function. That's all it's asking for. So y equals x would be your basic function. If I said y equals 3x cubed plus 2. All we really want to know is what's happening to the x, right? So in this case, we have an exponent of 3 on the x, so my basic function here would be the y equals x cubed function, which is our cubic function. So we're just trying to identify what that is. Okay, and they're going to give you a picture of it as well, so sometimes the picture is a dead giveaway, but for me, I think the easiest thing would just be the shape of the graph. One other one that you will see here This is the seventh one that I'm just noticing that's on here that we don't really see this one very often. Just to show you what this one looks like, because we would call this one the cube root function. We saw the square root function. This one's the cube root function, and it's going to go through here and kind of make a path that looks like that. Okay. So there's just tons and tons of different functions. We're going to talk about another one here in a little bit that's different than all of these. It's called the piecewise function, and that's something that's going to be new to you guys as well. All right. A couple of things that we're going to do with these functions today. First of all, here is another type of function. That's really what today is all about. All these different types of functions. This one's what we call a piecewise function. And this is one I was telling you, you guys have really never seen this one before, I don't think. This is not one that we really see in Algebra 2, so this is going to be kind of a new concept for you. It's a function that's broke up into individual pieces, basically. Okay? I'm going to show you what a graph looks like here in just a second and how we could graph it, because all the graphs are going to look a little bit different. But the first thing that we're going to talk about here is how to evaluate a piecewise function. Okay, so to evaluate a piecewise function, first of all, we're going to have g of x, which is going to be our function. And then you're going to see like this big bracket looking symbol. And within that bracket symbol, we're going to have multiple functions. Those are the different pieces. And sometimes it could be 2, sometimes it could be 3. You might even see 4, but typically 2 or 3 is going to be the most common that we're going to see. And then it's going to have a domain that goes with it for each function. And what's going to happen is all x values are going to be accounted for. Okay, so here is essentially what we're trying to do. If x is less than or equal to 1, this is the function that we're focused on. If x is bigger than 1, then this is the function that we're going to be focused on. All values of x are accounted for in some shape or form, but it just depends on which of the two functions that we're going to use. So you have two different pieces, and I got to use one of those two pieces. Okay? Now, we've done this before where we evaluate. And we're going to do 4 different evaluations here. We're going to take these 4 values, we're going to plug it into the function, and we're going to see what we get. Okay? And we did this a lot in chapter 1. But when we do it to a piecewise function, here's what we got to pay attention to. We're going to start with negative 4. Negative 4 has to fall in one of these two domains, right? Right now, negative 4 is less than or equal to 1. So this is the function that we're going to use. So we're going to take negative 4 and plug it into this one, and we're not even going to use the second one when we evaluate it. We're only going to use the first one. So we just take negative 4, we plug it in, negative 4 plus 4 is 0, so 0 would be my answer. When I plug in negative 4, 0 is what I get. Then we're going to go to 0. That's our second one we're going to evaluate. Once again, 0 is less than or equal to 1, right? So we're going to plug it into this one again. 0 plus 4 is 4. The math is not necessarily difficult here. We just got to make sure we plug it into the right function. And then we go 1. Okay? 1 is less than or equal to 1. We got the equal to sign here. Okay? So this is, once again, the function that I'm going to use. 1 plus 4 would be 5, and that would be my answer there. And then finally, 3. Okay? 3 is not less than or equal to 1, right? 3 is bigger than 1. So this is the function we're going to use now, because we're bigger than 1. So I'm going to take 3, I'm going to plug it in for x. 8 minus 3 would become 5. and those would be our answers, okay? I can plug any number in I want to. That could be fractions, it could be decimals. I'm just trying to pick a different range of numbers here to plug in, okay? And don't freak out if you get the same answer for your y values. That can happen, okay? Not always will happen, but it could happen. So that's what it's going to look like when we evaluate. Now graphing it is going to look completely different, okay? This is going to be the one that sometimes is kind of outside the box for us, okay? And so I'll try to explain this one to you and what this is going to look like. So they're going to ask us to graph a piecewise function. Instead of evaluating it, we're going to graph it. So here, once again, we're going to go g of x and I'm going to try to keep it pretty simple for you here, or as simple as we can anyway, when we do a piecewise function. And what I mean by that is I'm only going to probably just give you linear functions as a piecewise function, because we could do some that this one's linear and this one's quadratic, or this one's linear and this one's square root function or something like that. So I'm going to just try to keep it to all linear functions. So when I graph it, they're going to be lines, but they're only lines graphed on specific intervals. So we're going to graph this function, which we've graphed before, right? But we're only going to graph it for x values less than 3. So we're not going to graph the entire line. We're only going to graph it up to 3, not including 3. For this function here, we're only going to graph it for x values of 3 or more, okay? So it's not going to be a continuous line in both cases, like it has been in the past. We're only going to graph it on that specific interval that we're looking at. Okay, what I'm going to do here is I'm going to bring in, it'd be better I think if I used a piece of graph paper here. So we're going to graph this function for all x values less than 3. Okay, so if I were to graph that function, it's y equals mx plus b, right? I look at it and I have to decide what's my slope, what's my y-intercept. So what's my y-intercept? 3, okay? So we're going to go up 3. We're going to make a point. Okay, then the second number here is our slope, right? Our slope tells us we're going to go up 1 over 3. Now here's where you got to be careful. I'm going to put an open circle right here, because at x equals 3, we're not including it. It's not equal to, right? So we're going to put an open circle right here. Okay, this graph can go to the left as far as I want it to go. So instead of going up 1 and right 3, I could also go down 1 and left 3. And I can do that as many times as I want to, because this graph is now going to go to the left forever, okay? And I can make as many points on it as I want to, going to the left. But it's going to go up to this open circle right here and stop. It's not going to keep going, because we have to stay less than 3 for that line. So we've graphed the first line for all x values less than 3. Okay, questions on that? Does that kind of make sense? Okay, but that's our first piece. This is why we call it a piecewise graph. So now we're going to do our second piece. And we should put an arrow here to show it's going to continue on. Okay, now here's the one that's going to be a little bit tricky, okay? Negative x, but only for x values greater than or equal to 3. Okay? So what would be the y-intercept for this function? it'd be 0, right? So typically we would say we're going to start at 0, but I don't want to put a point there because I can't start my graph here, okay? So typically I'd put my y-intercept here as 0, and then my slope is -1, right? So from this point, we're going to go down 1, right 1, down 1, right 1, down 1, right 1. And that gets us to 3, okay? At 3, we can make our first point. And that's going to be a closed circle. And from that point, I can continue going down 1, right 1, down 1, right 1, as many times as I need to go. And then that graph is going to continue on to the right. So it's 2 linear functions that are going in different directions and starting at different points. But 3 is kind of the break-even point here. This one is not including 3. And typically, no, okay, we call this a function, okay? Let's go back to last chapter. When something was a function, and I looked at the graph, what did it have to pass? It had to pass the vertical line test, right? As I run my pen across here, does this function pass the vertical line test? And if you look at 3 right here, this one's an open circle, this one's a closed circle, so even at 3, it passes the vertical line test, because one circle is open, the other one is closed, okay? So at every point in this graph, it's passing the vertical line test. So it's still a function. It's just a piecewise function. All of the graphs that we're looking at today are functions. They all pass the vertical line test. So that's the one thing they have in common, is they are all functions. Okay, questions on that? It's a little bit different, okay? A little bit outside of the box of some things that we've done before, but just graphing it a little bit differently. Hey, one other one, you're going to have a story problem today. Okay, and I'm going to just kind of set this one up for you. We have a rectangular backyard. That needs 480 feet of fencing. Okay, and here's going to be the part that's a little bit tricky. Express the area as a function of its length, which is x. So we're looking to write an equation for the area in terms of x. Okay? And so here was what a lot of people would do. Because this is a rectangle, right? X is our length, so that is given to us. X is the length of this rectangle, yard, whatever we're looking at. And so then a lot of people would say, well, this is y. Okay, and that's not wrong. And so then they would say area is length times width, right? Which is still true. But this would be area in terms of x and y. We need to write area in terms of x. So what that means is we need to rewrite in terms of y. Well, when I find fencing, okay, if I was to put fencing around a yard or a dog pen or whatever it is that I'm doing, okay, then what am I finding when I do fencing? Perimeter. Yep, perimeter goes around the outside. Area is like how much grass I'm going to need inside of it or how much whatever you're covering, like carpet or flooring or something like that. But in this case, perimeter is on the outside and we have 480 feet of it. Okay? So what we're going to do here is we're going to say perimeter equals 2x plus 2y. That's our formula for perimeter, okay? So there's two formulas that we need here. This is my area, this is my perimeter, okay? We actually know the perimeter. It doesn't come out and tell us that it's the perimeter, but we know we need 480 feet of fencing. So we're going to plug 480 in for P. Okay, and the reason that we're doing all of that is because we want to express y in terms of x. I only want one variable in my function. And I got to express this in terms of x. If you think about all the functions that we wrote out at the beginning of the lesson today, they all had x, and we were doing something to the x. So they're all functions of x. They just were doing different operations with it. So what we need to do here is we need to solve for y. We're going to get y by itself. What would I do first in this equation to get y by itself? Subtract 2x, yeah. Okay, and what's a little bit weird or outside the box here is we can't actually subtract those two together because they're not alike. They're not common terms, right? So this is just a 2x here. 480 minus 2x. That's as simple as I can get. And then we got to solve for y. Okay, so to solve for y, and when I divide by 2, I got to divide everything by 2, all the way through. So 240 minus x equals y. So then what I can do is I can put that in for my width. My width is 240 minus x. Instead of writing it as y, I'm writing it in terms of x. So my length is still going to be x, but my width now is going to be 240 minus x. So we just have to get that y replaced with something that's equivalent using an x. And that's how we get it. And so at this point here, you could distribute that x if you want to, but I am totally okay if you just want to leave it like that and just say area. Because we've done it. We've written a function in terms of x. This would represent the area of that dog pin. Okay, now, you might say, why would you ever want to do this? Okay, I get it, right? But here would be a situation where you could want to do it. You want to maximize my fencing, right? I want to make this pin as big as I have, but I'm limited to 480 feet of fencing supplies, okay? And so you could make a lot of different, but you want to use as much as you can because, like, let's say you're making a pin for your dog. You want to make it as big as you can so he has as much room as possible. So I want to maximize my area inside that pin. And that's where you would plug in some different numbers here for x, for the length, and figure out what the width would have to be, okay? Or all I know is the length, and you could find what that maximum would be. So you could find different dimensions and you could plug it in. We're not actually doing that right here, but that's where you could use it if you wanted to. Okay, so a little bit different, but when it says write a function in terms of x, that means that's the only variable we want. We don't want an x and a y. We want just x, okay? And you could use L and W for length and width, but once again, I might say write an expression for area in terms of length, or L, and so it would be the same idea. So you're going to write a function in terms of one variable. Okay, that's all we got. Okay, that is 2-1. Okay, 1 through 8 are pretty straightforward. Those are just telling me which function we're using. 14 is kind of a story problem like what we just did. 19 and 20 are evaluation type problems. And then 22 and 25, you're doing a graph. Okay. If you would like a PDF